In this section, we're going to go over 30, 60, 90 triangles. And this is going to work really similar to when we did our 45, 45, 90 triangles. Yesterday, you guys did a Desmos activity, and you were kind of able to start to see that there's a pattern that also shows up on 30, 60, 90 triangles, just like we had a pattern for the 45, 45, 90 triangle. Okay, so let's just kind of review what we saw yesterday, and maybe even just taking it back a step, because I didn't really talk about this with you guys, but on a 30, 60, 90 triangle, you're not dealing with an isosceles triangle anymore. But where a 30, 60, 90 triangle came from originally was something called an equilateral triangle. Equilateral is meaning that all the sides are the same. If all the sides are the same, that means that all the angles on the inside would be the same as well. So some might also even call this an equal angular triangle as well. So your original triangle started out as a 60, 60, 60 triangle, and all three of the sides were the same. Now, where does the 30, 60, 90 triangle come from? Well, if I were to draw in a line that goes from like the corner of one of the angles, so I'm just going to come from this top 60 degrees. I'm going to go straight down to the other side. If I made a 90-degree angle here, I have my 90 degrees now, 60, and up here, this angle gets cut into 30 degrees on both sides of that 60-degree angle there. And that's where we get this 30, 60, 90 triangle that they have drawn off over there to the side. So 30, 60, 90 triangles come from half of an equilateral triangle. Now, just like we did with 45, 45, 90 triangles, on that Desmos activity, you guys had to use Pythagorean's theorem in order to help you solve for the missing variables, and you were looking for a pattern, okay? You were trying to figure out what is something that the legs all have in common, or what's something that we're noticing that allows us to make these problems a little bit faster. So if we just kind of really quick go through these examples down here, if you were going to do them like you did yesterday, where you're setting them up in Pythagorean's theorem, what would this first one look like? How would you put it in for your a squared plus b squared equals c squared formula? Okay, so 4 squared plus x squared equals 8 squared. Good. How would you set it up for the middle triangle? Okay, x squared plus 3 squared equals 6 squared. And how about for the last one? What would this one look like? Okay, and I would make sure you're putting parentheses around these quantities with the square roots, right? Yep, okay, so it's going to look like this. Good. All right, now then you would start doing the squaring, right? So like on this first one, you get 16 and 64. You subtract, you get 48. That's not a perfect square, right? So you had to break it down. How did this reduce? Or how would this reduce? Okay, 4 square root of 3, good. So that was this side here, 4 square root of 3, okay? Now over here, it's the same setup, it's just different numbers. So this would become x squared plus 9 equals 36. You'd have x squared equals 27, right? What would you get if you square root 27? Okay, so did you do the square root of 27, or did you start to see a pattern or something maybe from yesterday that helped you do that? All right, so you said because you saw that this little side here was 4, that the longer side is that same number, 4, but has a square root of 3 attached. And the same thing is happening on the second triangle here. Yeah, because we have a 3, and then this would be 3 square root of 3, and that's what we got, right? Yeah. And if you actually did reduce the 27, like if you weren't just going off of a pattern, it would still come out to be 3 square root of 3. So that's absolutely correct. Okay. Now, what happens over here? Because this is kind of complicated. What happens in this first set? Okay, so you got 32 because you took the 4 squared, which is 16, right? And then if you square root, that number just comes out. So 16 times that 2 would be 32. Good. And then if you do the same kind of thought process over here, what did you get? Yeah, that sounds right, 128, because 8 squared would be 64, and then times 2 would be 128. Yep. And so then if you subtract, you have 96. And then again, if you square root here, or if you're trying to use a pattern, you're taking this 4 square root of 2 and you're trying to attach a square root of 3 next to it, what would that become? Yeah, 4 square root of 6. So that would be this side. Good. Okay. So yesterday when you guys did this, we had some problems where they maybe gave you the shorter leg or they gave you the hypotenuse and you were able to maybe figure out that kind of third side that has that square root involved, right? But just like yesterday, or I'm sorry, just like a couple days ago when we did 45, 45, 90 triangles, there was a pattern. There was a definite relationship between those three sides that allows us to do this a little bit quicker, okay? So let's take a look at that down here. So a couple of things that I noticed when we did 30, 60, 90 triangles is that the hypotenuse was always equal to whatever the shorter leg was times 2. And my shorter leg was always going to be whatever your hypotenuse is divided by 2. Okay, so that was one kind of relationship. Another thing that we saw was that the longer leg was whatever the short leg is times the square root of 3. And again, if I wanted to go back, if I wanted to find the short leg and I had the long one, I would need to take the long leg divided by the square root of 3. So you can always go back and forth between the two legs depending on which one they give you. Now, if I'm coming over here to my triangle and I'm trying to label these, we first need to understand like what's the difference between the three sides. So again, if we know that our right angle is here, then we know that this side would be the hypotenuse. Okay, then I'm going to call this one down here at the bottom short, and I'm going to call this one long. Okay, now remember when I did the 45, 45, 90 triangles, I didn't use X's when I was talking about my pattern because that can be a little bit confusing when we start seeing X's in our problem. So if you remember, I used S's. I'm going to use S as well here. I'm going to start by calling my short side S. And then my hypotenuse was always 2 times the short side. So I'm going to say 2S for the hypotenuse. And then my longer leg was always the short side and a square root of 3. So I'm going to write that S square root of 3. That's a real general way that we can write out this pattern. So now using that pattern, let's figure out how we can solve these other problems maybe a little bit more efficiently here and not having to use Pythagorean's theorem again, okay? So just like I did with the triangles in the past, I'm going to label all my sides first. So the shorter side, that's always across from what angle? Maybe we could add that even up in here. This was 30 and this was 60. So your short side was always across from the 30-degree angle. Okay, so where that 7 is here, that's going to be your S. The side across from 60 is always S radical 3, and the hypotenuse is always 2S. Good. Okay, so since you know S is 7 here, what's Y going to be? What's the Y side? Good, 7 square root of 3. And what's your X side going to be? Good, 14. You just take 2 times 7. That's way faster than using Pythagorean's theorem, don't you think? So now that we have this pattern, let's continue to use it here to help us find these other ones. Okay, so look over here at this next one. What side are they providing us with? The hypotenuse. And what do we say the hypotenuse was always labeled with? Go to 2S. So what should I label the X side with? s, and then that means y has to be s squared of 3. Good. How would you, in this one, solve for just s? You would divide 10 by 2. So s is how much? Because you're doing this. 5. Good. So s is going to be 5. So the x side should be what? Good, 5. And the y should be 5 squared of 3. There you go. Now you can see how like that one was a little bit different. You weren't just provided with s. Sometimes they're going to make you work a little bit to figure out what s is. But so far hasn't been too bad, right? That hasn't been anything super complicated. All right, let's take a look at the next one here. Tell me where I should put my labels at. Like where should s, 2s, where should all that stuff go? Okay, s here, 2s here, good. And so this is s squared of 3. Okay, what is your s? How did you get that? Okay, so you're noticing here s squared of 3 would be equal to 8 squared of 3. If you were to divide by the square root of 3, they cancel. Okay, so you're saying s is 8. That's perfect. So what would x be? Good, just 8. And then this y would be, good, 16. Okay. Again, yes, I had to do a little bit more thinking. I wasn't just given my s outright. I had to maybe solve a little bit. But the way I solved it was pretty easy. Like I was able to just cancel the square root of 3's off and be done, right? All right, so now let's take a look at another one. And again, they're going to start to get a little more challenging now. First thing I want you to do, we had this happen on 45, 45, 90 triangles as well. I want to cross this off and I want to make this just 9 centimeters. Okay, and let's talk our way through here. So let's first start by labeling everything. So across from 30 is s. Across from 60, which is where I put that new 9, is my s squared of 3 side. And my y would be the 2s because that's my hypotenuse. Okay, now this time, I don't have just a real quick way to solve for s because I have s squared of 3 being equal to 9. How would you guys solve for s? Okay, so then these are gone. Can I leave that radical 3 in the denominator? No. What did we have to do when we saw that? Good, you have to multiply. So it becomes 9 squared of 3 over 3. What can you reduce? Good. So my s side is 3 square root of 3. Okay, so that's going to be my x. This one is just the 3 square root of 3 side. That's done. What am I going to do to solve for my y? I'm going to write it like this. What are you going to take 2 times? Why are you only taking it times the 3 and not the square root of 3? Yeah, because the 2 isn't underneath the square root, right? So we can't put those numbers together because they're different from each other. Think of it as kind of like the square root almost acts like a variable does, like an x. And I can't put that 2 times the x and have it become like a 10 because I don't necessarily know if those are the same thing. So I have to kind of keep it separated like that. All right. So that one was a little harder. You had to do a little bit more work, maybe. Maybe it wasn't hard math, but you had to work a little bit harder to get to those answers. Okay? Now, there's 2 more here on this page. I'm going to give you guys a couple of minutes. I want you to just see what you can do with both of them, and then we'll go over them together, okay? Okay, I'm going to start walking through these ones here. So I first would have labeled s squared of 3, 2s. So in this one, you have s squared of 3, and you're setting that equal to the 21 square root of 12. If you divide by the square root of 3 on both sides, they cancel off here. You can take the 12 divided by 3 and get 4. What is the square root of 4, though? A 2. So you're going to take 21 times 2, which is 42. So this side is 42, and then you double it for the y, and you get 84. So those would be your two missing sides. Okay, now something similar happens over here, except your s squared of 3 side now is going to be equal to the 5 squared of 6. What'd you guys get when you divided by the square root of 3? Good, you got 5 square root of 2 there, okay? So that would be your s side, which just means where the x is would be your 5 square root of 2. But remember, for your y, you have to double that. But kind of like what we saw in that first one that we did here on the bottom row, you only take 2 times the 5. So this should have been 10 square root of 2. Any questions on that? Oops, I just noticed I wrote s squared of 2. That should be a 5. Sorry about that. 5 square root of 2 up there. Any questions?